Swayam Prabha. Digital India. Educated India.
So this is the data. This is the true data, okay? And what is the weak learner? The weak learner I'm actually using is decision stumps. Are you aware of what decision stumps are? So decision stumps are an extreme version of decision tree where you have the decision tree with depth equal to 1. So you are going to decide based on just one feature and just threshold it. That means that the only types of classifiers possible are basically something like this. You have a line here and everything on this side is red and everything on this side is blue. And or you could have a line like this and everything on this side is red and everything on this side is blue. Only essentially you have a very small number of classifiers that are possible. You will see as time goes on, okay? So here I've set gamma equal to 0.2. That's kind of very aggressive, but I want to show fast progress. So essentially, if your gamma is really 0.2, if you set it to 0.1, it is going to still work, but the convergence is going to be slower. So it is better if you want fast convergence, it's better to set gamma higher. But if you are not sure your weak learner is going to satisfy that gamma, then you are in trouble. So if, for example, if you can always set gamma equal to 0.5, it is going to converge in one iteration, but it is going to converge to the wrong answer. That's the problem. So if you want to converge it to the right answer, then you must set your gamma low. If you want to converge fast, then you must set your gamma high. There is an interplay here, but for now, say we'll set gamma equal to 0.2. You'll assume that it's going to work, okay? So, okay, you do that. Now, what would a good weak learner be? So, what's a candidate weak learner here? Yeah. So, what's a weak learner? What's a good decision stump for this data? Either, do you want a horizontal line or a vertical line? Horizontal line. Say, then this might be this a good line, right? So, call this a horizontal line, and everything above this horizontal line is going to be red, and everything below this horizontal line is going to be blue. That's going to be my decision. Oh, sorry, I did the other way around. So I'm going to draw a horizontal line here, and everything below this horizontal line is going to be blue, everything above is going to be red. They are equally valid, right? So that's what you do here. So that's what your first weak classifier. Now it's unweighted data. All data is unweighted, so you just do this. Okay, so that's fine. Now, what has this classifier got wrong? Yes. These points it has got wrong. So that means that then the weight of these points must increase. The weight of all other points is going to stay the same. And that's what you will see. Can you actually see these? They are bigger circles than this. Can you see that? These are actually bigger dots than these. Okay. So now you have higher weights for this. Now I want to learn a weak classifier. What's a good weak classifier now? So these are, so essentially how much is it weighted by? It's weighted by 2.33. That means that these points now are worth 2.33 times these points. These points are now worth 2.33 times these points. So that's the beta role playing here. Okay, so now I want a weak classifier. So what would be a good weak classifier now? Horizontal line or vertical line? Once again, horizontal line will work, but just that now you do the other thing. In the previous thing, you drew a upper and you classified everything. Now you call this and call this everything above was red and everything below was blue. That's what you will do here. So that's what you will learn. And now, okay, so now what all have you gotten wrong now? These you have gotten wrong. So the weight of this must increase. So now, at the end of it, you have these 4 sets of points. Now you have had 2 weak classifiers. These points and these points, both classifiers have got right. The points, these 4 sets of points, one of them has got right, one of them got wrong. So that's the idea, okay? Now you want to once again, all these points are worth, this point is worth 2.33 times this point is worth 2.33, 2.33, 2.33. So these points are essentially worth 2.33 times those points, okay? Now we want a weak classifier. What's a good weak classifier now? Horizontal line or vertical line. Now assume that these are sufficiently heavy. This, instead of 2.33, say it is 100 for simplicity. What would you do now? Vertical line, yes. So, any vertical line is fine. So now this is the vertical line you choose. So essentially you choose to use this vertical line and everything on the left is red and everything on the right is blue. That's what you are chosen to do. And that's what you have done now. So now what have you got wrong? You've gotten this wrong. But in addition, you also have gotten this wrong, which you have never gotten wrong before. Both your two classifiers got this part right. But now this third classifier, in an effort to get something right, it has gotten that wrong. Okay, so that's the thing. So now the weight of that also will increase. So you can see that now this will be 2.33, this will be 1. So this everything has gotten right. This also everything has gotten right. This will be 2. What was the? This will be 2.33. This will be 2.33. This will be 2.33 squared because two classifiers have gotten this set wrong. So this will also be 2.33. So the weights never decrease. The weights always only ever keep on increasing. Okay. So now this point is worth 2.33 squared times this point, and this points are worth 2. So that's the idea. Okay. If you want the exact demarcation, it's like this. I don't know. Yeah, that's basically the idea. So you can keep on. So you can do a weak classifier now, and for this, now this turns out to be the best weak classifier. So now, okay, now we want to stop now, and what's the strong classifier? Okay, so we'll just go back here. Now you have learned all these weak classifiers, that's fine. But how are you going to combine them? Once again, the trivial way to combine them, what's the trivial way to combine them? Majority vote. That's the majority vote is the trivial way to combine them, and that's what you do. And if you do the majority vote, you assume you stop this iteration now, and you do a majority vote. This is what you would get. It looks not too bad in the sense that it gets these areas correct, and these areas correct. This area is kind of, it's saying white. I don't know what white means. It can either mean red or blue, but it does not matter. Anyway, it's saying these two are the same, which is wrong. They are both different. But more or less it gets gotten, essentially that's what you would guess, right? So in this data set, you can immediately say what is the toughest samples to get right? That would be these. Right? Those are the toughest samples to get right. And in just 4 iterations, it is doing, your strong classifier is doing well on all but those toughest points. Okay, so that's the idea. And you can keep on doing it. Okay, fine, it's not working, so I'll keep on doing it. So if you keep on doing it, so you can do data 5 will be this, 6 will be this, 7 will be this, 8 will be this. So you do a strong classifier at the end of iteration 8, it again looks pretty much similar. Okay. Oh, I mean, is it hopeless now? Is it always going to stay that way? It is not, because your weights are always going to keep on increasing. At some point you will see something like this. So because this set you've gotten almost always wrong, this has become bloated to such an extent that almost nothing else matters. Your next weak classifier is forced to get these two correct. Now all the others don't matter that much. Now, because now weights have multiplied by 2, by say about 2 every time, these are very, very wrong when compared to other things which are mostly correct. So now finally your weak classifier 9 is going to draw a line in the middle, which is going to be enough to distinguish between these two. And now if you say plot your strong classifier, you will see that this is light blue, this is light red. You can see that. So it's actually getting 100% accuracy now. Right. So that's the idea. So it's yeah. So it's as simple as that. So you can, I mean, there's no need to stop. You can keep on going, but you cannot get more than 100% accuracy. So you'll stop here. So that's the idea. So any questions on this? Okay, now we'll come back to the algorithm actually. So I don't think I'll be able to do a proof of the algorithm because I wanted to show that the mistake will actually go to 0, but that's not a problem. I can take it always offline. So this is the algorithm. The algorithm is now clear. I mean, when you just saw the algorithm, the notation is probably confusing you, but now you have something, an intuition of what's actually going on inside your mind. This is reasonably simple. Now you see what's actually happening and so on. So is the algorithm clear now to everybody? So the output, I'm just going to take the sign of, so it's plus minus 1. So if I add everything, basically it's the majority of the thing. That's essentially what you're going to take. Yeah?
Can we discuss on beta mode? What it is telling us?
Yeah, so that's where theory comes in, right? I mean, why is beta this? Why is it not just 0.5 plus gamma? Why is it not 1 plus 2 gamma? Why is it not gamma squared? Those are the questions, right? And that is where really theory comes you. I mean, this looks out of the blue. Why is this number coming? And that is where theory is going to help you. I mean, this looks strange. Why is this 0.5 plus gamma plus by 0.5 minus gamma is coming there? And that comes from theory. So that is where, I mean, that's a very crucial thing. I mean, if your beta is very high, you will be very aggressive in increasing the sample weights, and that might be wrong. If your beta was very low, you'll be very conservative in raising your weights, and that's also bad. So essentially, you want the right beta, which is neither conservative nor aggressive. And to get that, you need theory. So that's the reason where, I mean, I think this, I had planned it so that it segues nicely into the learning theory part of it. So algorithms are one part, but without theory, you can't set these kind of parameters. These parameters are actually very important to this intuition you could have gotten even by like, yeah, I'm going to build classifiers which are going to emphasize on the previous classifier's mistakes. This idea is simple. It does not require theory. But how much are you going to emphasize? How those numbers are once again strange, right? So those numbers you have to get by theory. So if you have time, I'll go over theory. But even if you don't, you can always go through it. It's not a problem. Yeah. Any questions? Any other questions? Okay. So I don't think I'll be able to do the proof on the hands, but I'll just, yeah.
So the first line reads that weak learners have greater than accuracy than 0.5.
Yeah.
If I had some weak learner which has even worse
Uh-huh.
than that,
So that's a very good question. I was planning on segue into that after the letter. So I mean, if it's just 0.5, then you can't do anything. But if it's gamma, essentially what you can say is, I know it can do better than random, but that gamma can go arbitrarily close to 0. That is the standard assumption that. So your algorithm should take care of that. That's the idea, and you can do that, and that is basically AdaBoost. So that's called adaptive boosting. So this boost by majority is you are assuming that your weak learner has, say, if gamma is 0.1, that means that if gamma is 0.1, I'm saying that I can give any weighted sample, and I can achieve 60% accuracy. What if that's not true? What if my weak classifier is so weak that it might work well on most of the weights, but if I give some weight, you can't achieve 60% accuracy. What if I do that? But it can still achieve maybe 51% accuracy. The one thing to do is, okay, maybe set gamma to be 0.01 instead. That's okay. But then what if 51 is too much, but I can achieve 50.9? Then what? So, I mean, you don't know that, right? So you ideally want this gamma to be adaptive. And that's basically adaptive boosting. So you have your gamma set, so that will come if we have time. Or I think I can also, because this is actually practical learning theory, I can also use this same proof. If you guys are interested, I can also actually segue into AdaBoost, which is also theory, really. It's I can do that also if you want. Any other questions? Both your questions actually segue nicely into my future in the next slide. So it's okay. So this is the idea. Okay, the thing that you consider is basically your total weights that you maintain. Okay, that's you at every iteration you just consider this object. So don't read the entire thing. Just read with me. Okay. So now you just consider the total weight. So at the first iteration, it's going to be the total number of samples. Because every sample has equal weight, it's going to be equal to m. If m is the number of samples, it's going to be equal to m. But every iteration, the weights are only going to increase. It's definitely going to increase. Because I'm never decreasing the weights, I'm only increasing the weights. So this is the idea, okay? Now you will actually bound this quantity both above and below, and that will essentially help you. So here's the idea, right? So if your final classifier H makes m mistakes, okay? And because you're using majority voting, H is simply, H is your final classifier. And because you're using majority voting, that means that at least T/2 of the weak classifiers must have made mistakes on the same points, right? Otherwise, why would you, because it's a majority voting, that means that your T/2 of the classifiers would have made mistakes. And weight of the sample goes up by a factor of beta in step T if mistake is made, and weight of the sample stays the same otherwise. So that means that the total weight must at least be m times beta power T/2, right? So forget the m for now. Take one sample on which you are making a mistake. That sample's weight must have increased at least T/2 times, because you have T/2 classifiers are making mistakes on that point. That means that sample's weight must have increased at least T/2 times. So that particular sample has a weight of beta power T/2 at least. It can be greater, at least beta power T/2. And you have m such samples. You are making m mistakes, so it's m beta power T/2. So your total weight is at least this much. Okay, so that's the idea. Okay, that's fine. Is this clear? If not also it's fine, but this is the idea. So you understand the logic behind these two steps, because here I'm using the fact that the final classifier is the majority classifier. That's what I'm really using. The next step, I will use the fact that each of the classifiers are actually weak learners. Here I have not used that actually, right? I mean, that's the next thing. Okay. So the next thing is basically is a little bit more algebra, but it's not really complicated at all. So you have your zt plus 1. So consider the total weights at iteration t plus 1, which is basically sum over I equal to 1 to m wi t plus 1, right? So I'm going to split this into 2. At iteration t, say you have a set of the set of samples your ht got correctly. You have ht is the iteration as the use your weak classifier at iteration t, right? So say you have the set of samples for which you got ht got the right answer. You call that a, okay? And so that means that I can just write this as a split sum. I mean, I'm writing down this a times a and beta, right? So for a, the weight is not going to increase. At wt plus 1 is going to be the same as wt. Because I've gotten it right, the weight is not going to increase. But if I is not in A, the weight is going to increase by a factor of beta. Right? So that means that for I not in A, it's going to be beta times WIT. So it's all equality. So there is now no bounds hereafter. Okay? And here is where you use the fact that what is the weak learner assumption actually really? So that means that if you give a weighted sample to your weak learner, your sum over I belong to A, Wi is greater than or equal to half plus gamma times sigma Wi. Right? Is this clear? I mean, maybe. So what is your weak learner guaranteed to do? It is guaranteed to do at least gamma better than random. That means that what is the total number of samples it got right? Total weight of the samples it got right? It's basically sum over I in A, Wi, right? That's the total weight of samples it got right. So this is at least half plus gamma of the total weight. That's basically it's greater than or equal to half plus gamma sigma over I Wi. The total weight of the samples it got right is at least half plus gamma of the total weight. So that's the weak learner assumption actually. So I can use that. And if I use that, this means that this is greater than or equal to 0.5 plus gamma WIT, and this is just 0.5 minus gamma WIT, and I can do that. And here is where your beta of 0.5 plus gamma by 0.5 minus gamma comes into the play. Because now beta is 0.5 plus gamma by 0.5 minus gamma, this 0.5 minus gamma cancels out, and you can take 0.5 plus gamma outside, and you get 1 plus 2 gamma zt. That means that in every iteration, your zt plus 1 does not grow by more than 1 plus 2 gamma as a factor. So if you have at the iteration 1 it was 10, your zt was 10. Sorry, at iteration t zt was 10, and iteration t plus 1 zt plus 1 can be at most 1 plus 2 gamma times 10. Say gamma was maybe 0.2, in which case it can be at most 1.4 times 10. So that means that zt plus 1 cannot grow too fast. That's what is essentially saying. Your zt cannot grow, as the number of iterations increases, zt cannot grow too fast. But you have this that zt is at least this much. Zt is growing fast. That's what this is saying. And zt cannot grow too fast. That's what this is saying. And you can basically put those both together, which is basically your zt plus 1 is greater than or equal to, zt is growing fast, but zt is growing slow. So there are two contradictory statements, but both are true. Right? That means that you can put them together and you will get this. That means that your m is your total number of mistakes. Total number of mistakes is less than or equal to m times, this is just algebra, don't worry about it. It's 1 minus 4 gamma squared power t by 2. So if gamma is greater than 0, 1 minus 4 gamma squared is going to be less than 1, right? That means that every iteration and power t by 2 is there. That means that even if it's 1 minus 4 gamma squared is 0.99, 0.99 power 1 million is going to be practically 0. Say, don't need to, you need to go to 1 million. Even for 0.99 power 1000, you're going to get 0. That means that your total number of mistakes is going to go to 0 as your number of iterations increases. And this is where the fact that you had to use beta equal to 0.5 plus gamma by 0.5 minus gamma was actually used, because that was actually crucial here. That's what allowed you to take your 0.5 plus gamma outside, and you can do this. So that's where, I mean, this is to illustrate that theory plays a very, very fundamental role in algorithms. Algorithms and theory don't exist separately. So theory and algorithms are easy to understand, but theory is where you actually get, I mean, if you didn't know this, would you try brute force over all possible betas? I mean, is that a valid thing? I mean, it's not a viable hypothesis. So that's where theory comes into the rescue. Okay. So maybe I'll just introduce ADA boost. Okay. So what is the issue with boost by majority? That's exactly what I didn't get your name. Nikhil. Yeah. So I mean, this is exactly the issue that Nikhil raised. So now you see that the algorithm actually uses gamma. What if you don't know gamma? You know gamma is greater than 0. Say somehow you know that gamma is greater than 0, but you don't know gamma. Then what would you do? So it requires a bound on gamma, and that's essentially you need to know how good the weak classifiers are in advance. That's what you need to know. And maybe you don't know that. What would you do then? And the problem is if gamma is set too small, the algorithm will converge slowly. And if it is set too high, the convergence proof will not hold, and it can just as well. So this also, I will try to show this in the lab part, where you will actually implement ADA boost, and you will set gamma. I mean, you know the true gamma, but you will actually set either gamma to be too low or too high, and you will see the convergence either too slow or converging to a wrong answer. You will see both of these, hopefully, if we have time. But that's the idea. So can we do better? And that is where your adaptive boosting comes in. So it's more or less the same, but just that now you are going to calculate gamma for every weak classifier. So, I mean, you have the weak classifier, you may just as well calculate how much it is better than random, right? I mean, you have the weak classifier. Instead of saying that, I want this classifier to be, say, 0.1 better than random, I can just as well calculate how much it is better than random. That's what this is. Don't forget about the math there. What this gamma t is telling is how much is ht better than random. Which is what gamma was, but now we have gamma t. Now we have a dependence on t. It is possible that at iteration 1 you have very good gamma. You might have maybe even an edge of 0.4 or 0.3, but at maybe iteration 20 you can only have an edge of maybe gamma to be even 0.01. It's possible. So now you have a gamma dependence on t, and you have a beta which is simply 0.5 plus gamma t by 0.5 minus gamma t. That's not a problem. Everything else goes through, but there is one slight twist. It's no longer majority voting. You can see that if you do this, but keep on doing the majority voting, you will run into an issue. That's basically that, for example, say, take the extreme case. Your first classifier was extremely accurate. It was almost, say, take the extreme case. Gamma 1 was 0.5. Okay. If gamma 1 was 0.5, what would happen is beta would actually be infinity, right? That means that you would, at the end of iteration 1, you did iteration 2, all weights would be all over the place. They would be unstable. It would be unstable, and that's kind of recipe for failure. But you don't know that. You run it for say 10 iterations. Actually, you could have just stopped at 1 iteration, and you could have just taken the first classifier and ignored all the classifiers 2 to 9. But now, because you're doing majority voting, you will also consider, I mean, essentially you have to make a decision on physics, and the first person you ask is Albert Einstein, and then the next, the 9 person that you ask are maybe people who failed LKG. Okay, so that's what you ask, and then you take a majority vote of that. Right, that's not really going to work. Okay, so that's the extreme example, and in this case, you have to weight the classifiers accordingly. So in this case, you would give a weight of infinity to Albert Einstein, and everyone else give a weight of 0. That's what you would do, and that's what it essentially does. So you give a weight of log 1 by beta t. So you don't need to get the exact formula of it. I mean, once again, these numbers you get only from theory. Why is log 1 by beta t coming there? I mean, that seems strange. I mean, you can guess that it's going to be, if your beta is high, that means that you need to give low weight for this and so on. So that you can guess, but how high, how low, that once again comes only from proper theoretical analysis. And yeah, I'm not going to give that proof, but it's the philosophy is same. The proof techniques also almost exactly the same. You just bound the total weight of the samples. You bound it from below, you bound it from above, but just that now it's no longer majority voting, so it's not going to be, this is not going to be as simple. So you have to take into account that it is not majority voting. But that's basically it. So any other questions? Any questions on this? So yeah, I did boosting entirely for binary classification. With learners that actually output either +1 or -1, but you might just as well have learners that output a probability of a class. It need not just output +1 or -1. It can say it is +1 with probability 0.7, -1 with probability 0.3. You can extend boosting to work with that. That's why that's the reason you have this modulus of ht minus xi minus ya in the first place. I mean, if it's ht is going to be either just +1 or -1, this seems overkill, right? I mean, but it will work even if you have learners that output probability of a class. I will also work with multi-class learners. I mean, this was just binary classification. You can also have multi-class. It requires modifications, but it is possible. And there are other reweighting schemes. The problem generally with AdaBoost is that it is not very robust to outliers. I mean, I'm not defining what outliers are for you now, but it's essentially it's a problem that you will encounter, and there are other reweighting schemes. And because the weight explodes exponentially, right? I mean, every time you get it wrong, you are multiplying by something, and that's a very, very unstable situation. I mean, it can clearly, I mean, even if you run for 100 iterations, you might actually hit the floating point limit, right? So that's not a very good situation to be in. You have gentler methods which increase the weights slower. So these methods are more robust to outliers. For example, they are called maybe logit boost and so on. But they are more complicated to analyze than AdaBoost. So, but AdaBoost is the, once again, AdaBoost is a very popular learner. It's something which you will see often. Yeah. And say for references, bagging and random forests Leo Bremen was the guy who introduced and popularized both of them. And boosting was introduced in a set of papers by Yoav Freund and Robert Shapire, almost independently, but then they collaborated together in the late 90s. So they're classic papers in machine learning. So that's basically it. We can break, or if you have any questions, we can ask. If you have no other questions, we can wrap up for this session and can have a break.